Hello, my name is Jim Johnston, and I'm going to talk to you today about McElroy optimized cooling and the optimized cooling process. Specifically, we're going to talk today about ASTM F2620 with McElroy optimized cooling. Now with this, I want to start by taking us back and going through a little bit of history so we can understand how and why we are where we are today. So if we jump back in time and go back to 1994, prior to that time, all of the pipe companies had their own procedures for fusing pipe. In 1994, DOT, what we now know today as PHMSA, came to the Plastic Pipe Institute to ask if there was a way to make a single fusion procedure for the industry. PPI started that work, and what their work became is what we know today as TR33. Now, this process was really a harmonization of those procedures that were being used. TR33 was made with the intent of developing an ASTM standard, which ultimately resulted in F2620. The testing and validation process in TR33 focused on the pipe sizes, the temperature, and the pressure ranges that were used in all of those varying procedures. Now, if we look at this basis, we will see that it is a very conservative approach. When we take a hard look at and see how they were done, we can look on what and how these procedures were developed throughout the globe. Globally, procedures for fusion of polyethylene pipe have a broad range. They have temperatures that range from 390 degrees to 464 degrees Fahrenheit. And they range in pressures from 14 psi all the way up to 150 psi. Now, TR33 tested and validated using a box. It went from 375 degrees all the way up to 475 degrees and had pressures that range from 50 to 100 psi. Within all of that window, they had 0 failures in their testing range. Now, the resulting generic procedure that was developed from this TR3 testing, which became F2620, uses 400 to 450 degrees and 60 to 90 psi. And in general terms, most of the folks that are out there today are using right in the middle of that box, 425 degrees Fahrenheit plus or minus, and 75 degrees psi. So it's a window inside of a window inside of a window, a very conservative approach. Now, as I said, both the TR33 and F2620 procedures are a harmonization of that work that was done. The key piece that was not reviewed at the time was looking at the time. So optimization is needed. Now let's take a look at the process for an 18-inch DR7 pipe. The F2620 cool time is roughly 28 minutes. That's the most significant area for affecting the total time of a fusion. And what we did was dive into that optimization, looking at the area that would make the most effect on the process. Now, over the years, McElroy has been approached by users, and we've looked at ways to streamline and bring efficiency to the joining process. Look no further than our Trackstar line, our poly horses, pipe stands, and a myriad of other products. As a manufacturer, we wanted to focus on continuing this work to help bring efficiency to the process, and we wanted to build something. We started with testing in mind and found that a variety of things we had tried had very little effect on the cooling curve for the core temperature of the wall of the pipe. As we look back, this really shouldn't be a surprise. HDPE is a poor conductor, or said differently, it's a great insulator. So let me show you an example. Let's start with a really good polyethylene cooler full of beer, seal it up, and then blow a fan on it. Is that fan going to change the temperature inside the cooler? No, it's not. In the same way, we found that even extreme cold had very little effect on the middle of the pipe wall. If we look at it just a little bit differently, how many of you have gone outside on a hot summer day to water your lawn or plants and been burned by the sidewalk? What do we usually do in that case? We spray the concrete under our feet to cool it off. But does that last? Again, no, it doesn't. The heat of the concrete will soon come back and come up through the system. We've seen very similar things. You can cool the OD of the pipe, but you're really not affecting the core of that pipe wall. Now, we've done extensive testing, hundreds and hundreds of joints, in fact. We've also involved our pipe industry partners and many, many others out there in the world. So let's take a look at our progress so far. We first introduced this concept at Infusion 18 here in Tulsa, Oklahoma. We presented at Plastic Pipes 19 in Las Vegas. We've done presentations at the OzPipe show in Sydney in November of 2019. And we have been doing validation after validation after validation testing. Long-term testing, short-term testing, all kinds of testing. It's been all about testing and validation. From these hundreds of joints we produced, thousands of data points. We've done test pulls, we've tested temperature variables, we've done short-term tests, McSnapper tests, bin back tests, guided side bin tests. We have ongoing long-term tests in process. We've looked at those temperature variables again and OD and wall thickness combinations. We've performed computational fluid dynamics modeling to produce an algorithm that helps us predict the core wall temperature and therefore a consistent point at which we know we have the strength to handle the joint. So what do we know now? We now know from this graph represents a typical set of cooling curves for a fusion joint. On the y-axis, we have temperature of the core of the wall of the pipe, and on the x-axis, we have pressure. Note that the temperatures are a very fast drop from fusion temperature to the onset of crystallization. The following drop in temperature from that elbow is very long and slow. As a result, the slope of that curve shows that one can reduce the cooling time significantly without changing the wall temperature very much. With this data, we can predict a high degree of certainty the pipe temperature and therefore the strength of the material at any point on this curve. Now, throughout all of this testing, we took into consideration a number of variables that are seen in the fusion process. What we found is that 4 variables have the largest effect on the core pipe temperature itself. Those are ambient temperature, bulk pipe temperature, or the pipe temperature itself. PPI studies show us that solar-loaded black pipe can reach temperatures of 150 degrees Fahrenheit or even higher. And that has a significant effect on the cooling of the pipe itself. The heat soak time, how long that pipe is on the heater and producing a molten area on the pipe. This is critical, as important as the amount of heat into the system must be dissipated. And to no one's surprise, the wall thickness and the OD have a strong effect. When we started this, I stated that this is compliant with ASTM F2620. Now, ASTM F2620 has a note in the butt fusion procedure that allows for a controlled cooling cycle. Due to revisions in the standard, this note will be a different number depending on the revision and year of the standard you use. In F2620-12, it's note 8. In F2620-19, this is note 10. In the next edition, that note may be a different area. McElroy optimized cooling is compliant with this note in F2620 that allows for a controlled cooling cycle. Now, McElroy optimized cooling will only be available in the Data Logger 6 and following Data Logger devices. It will not be available in McCalc or any online form because there is live data to be entered on every joint. On the data logger itself, you're going to see that this is listed as ASTM F2620 with McElroy optimized cooling. Again, it is only going to be available in this area because we are going to require live data entry throughout the process. So now let's look at some specific data. Let's take a look at a 36-inch DR11 pipe at 75 degrees temperature. So a standard fall day with very little solar loading. The pipe is 75 degrees, the air temperature is 75 degrees. Everybody's happy because we're cooling on the most optimal day that we can. The minimum cool time per F2620 is 2,160 seconds. That's 36 minutes. With McElroy optimized cool time, that time, that cooling time, can be reduced to a minimum time of 985 seconds. That's just under 16.5 minutes. All in all, it's a 54% reduction in the cool time. Now let's take a look at how the impact of wall thickness, varying the DR. So I'm going to change this to a DR9 and still look at a 75-degree temperature. The minimum time is 2,640 seconds per F2620. That's 44 minutes. With McElroy optimized cooling, that can be reduced to a minimum time of just over 1,200 seconds. That's just under 16.5 minutes. It's a reduction of 52% in the cool time. Notice that there is a reduction in the percentage of the cool time because of that thicker wall. It does have an effect. There is more mass there. It takes longer to cool. But it is a significant reduction in that cool time. And in all of these cases, our formula is calculating a time that gives you confidence in the strength of that joint. We are predicting a temperature at the core of that wall of that pipe that gives you confidence in handling that material. Now let's take a look at throwing in some higher ambient temperatures and pipe temperatures. Think about West Texas. It could be mid-60s in the morning and high 90s in the afternoon, or even higher. And black pipe could reach temperatures of 130 to 150 degrees. We found in our studies that there is a critical difference and must be accounted for throughout the day. Using our same example of 36-inch DR9 pipe, we can see at temperatures and higher pipe temperatures, a longer cool time is required. The ASTM standard, again, 2,640 seconds. At 75 degrees, 1,251 seconds. At 95 degrees, that jumps up to just over 1,300 seconds. And at 120 degrees, it jumps up to just shy of 1,400 seconds. Ambient temperature and the pipe temperature itself is critical in the process, and it needs to be accounted for throughout the day. These minimum times give us the strength characteristics to be handled. So let's take a look at some production examples. What does this do? What does this really mean for me in terms of production? Let's take a look at a 20-inch DR9 job at assuming, let's say, the pipe temperature is 95 degrees, an average 95-degree temperature day. A 10-mile job is 1,060 50-foot sticks. Using the minimum cool time called out in F2620, this job will have 432 hours of just cooling time. With McElroy optimized cooling, that cool time can be reduced to 339 hours, a saving of roughly 93 hours. Now that isn't just operator time though, that's helpers, pipe handlers, lift operators. So you can take that 93 hours and increase it from there. So 93 man hours plus all of your support equipment. This can make a job more productive, more competitive against other materials. It can be used as a differentiator with the data logger. Now we know that people are reducing their cool time today because we see the data, but they are not doing this with any consideration to pipe temperature or these other critical variables. With the data logger and this process, you have confidence in achieving a consistent joint and document that the process was followed no matter what the wall thickness, ambient temperature, or pipe temperature are throughout the process. Remember, total man hours equals a reduction in all the other people involved in this job. Now, one of the things that comes up in any fusion discussion is the definition of rough handling. The prohibition on rough handling is important on every fusion joint and every fusion procedure, no matter where you are in the world. Whether you use McElroy optimized cooling or not, you should always follow best practices when handling a fused joint at the end of the cooling cycle. This includes using handling equipment, rollers, pipe lifts, poly horses, poly porters. No single point lifting. Don't use a single basket or choker to lift the joint out of the machine. You should have multiple lift points to prevent giving kinking or any other kind of severe bending moment at the joint. and no excessive pulling on the joint itself until the rough handling cool time is complete. With that, we're going to close out today's session and ask for any questions that people may have. Again, McElroy Optimized Cooling gives you an opportunity to know that you have achieved a strength in that joint and given a minimum cool time that will give you a consistent joint strength, joint after joint, given the variables that are used to enter there. So we're going to enter ambient temperature, pipe size, OD, wall thickness, ambient temperature, and the heat soak time throughout the process. With that, McElroy Optimized Cooling gives you a very reliable and repeatable joint on every single option.